Hello everyone and welcome. My name is Jason Gregerson. In this video we're going to talk about applications of integration. And so we're going to go through several applications, but really what I want the focus to be is on the general approach to tackling these type of problems. So to outline our general steps, we're trying to figure out some value. We're going to call it V in this case. And the problem is that V is hard to calculate because something inside is changing. Maybe the height is changing, or the density of something is changing, or the probability of some event is changing. But whatever it is making it hard for us to calculate V. So what do? We look at our value over some small interval of time or some small distance interval, and in that small interval we're able to approximate our value. And once we have that formula for our approximate value in our slice of V, we then add up all of our pieces continuously to calculate the general V. Alright, now what does it actually look like in detail? Well, let's take a look at a specific example, area under a positive curve. So here's my problem. I want to find the area under this curve, y equals 2 sine of x plus x on the interval from x goes from 1 to 5. And so what is my process going to look like? Well, I'm trying to find the area under the curve on this interval. And the area is hard to calculate because the height changes throughout our region. So what do? I look at a small slice of the value. Some small slice, which I'm going to call a little slice of the area. Now if I look at just that small slice, the height is constant or approximately constant. So I might say the area of this little slice is approximately the function evaluated at that slice, some spot I, times the thickness of my slice, which is a little change of x in this case. So now I've been able to approximate the value of an area in one little slice. Well, then what do I want to do? To approximate the total area, I would then add up all my slices. But I want the exact value, and my value will get bigger if I look at the limit as my slices get smaller and smaller. And then I recognize the limit of this sum is the definition of a definite integral. So the total area is really the integral of that integrand as x goes from 1 to x equals 5. And so in this way we've modeled this approach using the Riemann sums. Now to kind of generalize this approach, I could really look at a small slice of area as dA. And once I define it to be my function height times dx, in a lot of ways I can think of this process of taking the sum and then evaluating the limit as adding up all my slices continuously. And I can use the idea of the integral there. So now I've gone through this process to set things up. Now I can just calculate this value in Mathematica. So now to calculate the area under this curve, all I'm going to do is integrate from 1 to 5 my function with respect to x. And I could use this fancy notation that I can get from the palettes, or I could use the integrate command in Mathematica like this. And remember, if I want to get a decimal value, if I put a decimal in, I'll get a decimal out. So now I have a value of 12 for the area of this curve, and I can verify that graphically as well. Maybe just by looking at some sort of rectangle that kind of lies inside here, and say that rectangle has a height of 3 and a width of 4, so the area of that rectangle would be about 12. And I'm a little over here and a little under here, but somewhere in the neighborhood of 12 seems like a reasonable value. Alright, so that's our first application. Let's look at another application, the area between two curves. So now we want to find the area bounded between these two curves, y equals 2 sine of x plus x like we had before, and the other curve is y equals x minus 3 quantity squared. So let's follow that same general approach. I don't have a formula for this in general, so I'll cut a small slice of this value I'm trying to figure out. I'm going to call it dA. In this case, I see the area of that little slice of rectangle will be the height times thickness. In this case, the height will be the top function, my f of x, minus the other function, my g of x. That's the height. I multiply by a little change in x as the base of my rectangle, and now I've represented my slice with a formula. Then to find the total value that I'm looking for, the area, I add up all my slices continuously. In this case, I'm integrating over what interval? Well, that'd be a little bit trickier in this case, so I'd have to use some other techniques in Mathematica to find these two intersection points, which should give me my limits of integration. So now I have that general flow to set up the problem. Now let's actually work the details out of Mathematica. So the first thing I want to do is calculate the intersection of the two curves. And we've seen that we can use the solve command or the find root command to do that. In this case, I'm going to use the find root command. I want to find out when my two functions are equal, making sure that I use the double equal sign. And then my variable is x. And I have to give my algorithm a starting point for this numerical technique. Now I could do a starting point of 1 and find my first intersection point, or a starting point of 5, which might find my second intersection point. Or I could actually put a list of starting points, and Mathematica would run this algorithm twice using each starting point and return each value. So I want to store these values. These are going to be my limits of integration. And there's lots of ways I can store these values. I could use some fancy code, or I could really just edit my output as well. So if I let the first output equal A and the second one equal B, and then I evaluate this, I can store my limits into A and B. And then, as we modeled in the setup, to find the area between these two curves, I would integrate my f of x minus my g of x from x goes from A to B. And there I have my value is the area between these two curves. Let's look at our next example. The next example is the mass of a lamina. So consider a thin metal sheet that's cut to be this shape that is bounded between my two curves. I would like to find the total mass of that shape if I'm given a density function where the density is equal to 2x grams per square meter. So now my new problem is to find the total mass. Well, I don't know how to calculate the total mass, so my general process says, let's look at a thin slice. So the problem is that my density changes throughout my interval, throughout my sheet here. But if I look at a small enough slice of this sheet, well, then the x value isn't changing very much inside this slice, so the density is almost constant in this thin slice. So now what I want to do is say, how do I find a formula for just the mass in this thin little slice? Well, if my density function is 2x grams per square meter, then if I multiply that by an area value, by the area in my thin slice, it should give me the mass in that thin slice. But in the previous problem, I've already seen that the area of that thin slice is just the height of the function at that point times the thickness. And so now I've set up a formula for the mass in one little slice of area. Now to find the total mass, all I do is add up all my slices continuously. And that's the general process. Now we can calculate this value in Mathematica. So now I'm going to integrate, and I'm going to integrate my density function times the height, which in this case is my f of x minus g of x, just like we had before. And I'm integrating that from x goes from A to B. And so now I have a value for the total mass of this thin metal sheet. One more application. This application is the volume of rotation. So now we'll look at that original area that we looked at, the area under the curve of 2 sine of x plus x. But now I want to take that area and rotate about the x-axis. Now just to see what that looks like visually, I can set up this manipulate and watch it. So here as I change my theta value, I'm rotating that area about the axis. And it's generating this object. And I'm trying to find the volume of this object. So what's my process? I need to cut a thin slice and try to find the volume of just that slice. So if I cut a thin slice, we can see that that thin slice would actually just look like a cylinder. And if I wanted to find the volume of a cylinder, my thin slice is the volume of a cylinder, well, the volume of a cylinder should be pi r squared, the area of the base of the cylinder, times the height of the cylinder. In this case, the height of the cylinder is a little thickness of my slice. In this case, I can see that's going to be dx. So what about the area of this circle? Well, this circle has a radius that I can sketch in right here. That's my radius value. And in general, that would be changing throughout my interval. But if I look at a thin enough slice, that's just the the height to the function inside of my slice, I can represent that as just the function evaluated at some point. So now I have a formula for a thin slice of volume. Then what do? I add up all my slices continuously, and now I have a formula for the volume. And now that I have my formula, I can just do the calculations in Mathematica. I can integrate 2 pi times my function squared. And I'm integrating that, adding up all those slices as x goes from 1 to 5 in this case. We get some sort of output, and as always, if I put a decimal in, I'll get a decimal out. Now I can see that the volume here is 251 cubic meters. Once again, the important thing is the general approach. We're trying to calculate some value. What we do is we look at a thin slice or a small interval where we can approximate that value, and then we set up the Riemann sum or add them up continuously, setting up the integral to calculate our value. All right, that concludes this video. Thanks.